Okay. Hello to everyone. So today we'll go over recursive definitions. It's section 8.8 recursive definitions, and we'll see how far we get. Maybe we'll get to structural induction, but I doubt it. Okay. I mean, yeah, because okay, but we'll see. The lecture today will be on this whiteboard, if you will. I call it a whiteboard. Okay. So here is a refresh of different recursive types of recursive definitions we already saw, and let's see with the let's start with the following examples. So let's say you want to define powers of 2 as a function. Okay, so you can do it like this. For, let's say, it's a power for non-negative integers, so, or positive integers. So let's say your base case is 1. So you define that the first power of 2 is 2. Okay, 2 to the 1 is 2. And then in a recursive case that goes for all n greater than 2, you can define this function recursively like this: fn is 2 times fn minus 1, right? So recursively, this defines fn at any n. How so? Well, here is the closed form. What is it? So fn is, we start with 2. For every time we increase n, it's like one more multiplication by 2 of the previous value. So these multiplications accumulate, and it's n times. So this is going to be 2 to the n, right? And we can use induction to prove this, right? Because, well, in the base case, n equal 1, that's true. This is 2 to the 1. And in the recursive case, if this is 2 to the n minus 1, then multiplying it by 2 clearly gives us 2 to the n. So the formula, if the formula is close about this guy, then it's close. If it's true about this guy, then it's true about this guy, which is an induction. Okay, so that's an inductive proof that this is a closed form. Okay, now let's look at this same thing as a sequence. So this had a special name. We called it recurrence relation. Okay, it simply recursively defines sequences, but in terms of, in case of sequences, it's a special term for that. So how did the recurrence relation that defines the same thing would go? Okay, so like first element of the sequence is 2, and for every n after that, the nth element of the sequence is twice the previous element, right? And because it's exactly the same thing, well, clearly Sn is 2 to the n, and the inductive proof that this is true is exactly the same as the proof before, right? It's true in the base case. 2 to the 1 is 2, and this is very easy to show, right? That if this formula holds about this guy, so in other words, this guy is 2 to the n minus 1, then multiplying it by 2 gives you 2 to the n. Okay, it's the same argument exactly. How about same thing as a recursive algorithm? Okay, so how did it look? Well, not in this visually, not in these separate things, but as a single code, but you know, just a visual thing, right? So let's say we have an algorithm power 2 with input n, Okay, and what would it look like? Well, if n is 1, so we have hit the base case, we return 2, and else and else you return what? 2 times power 2 of n minus 1, right? So that's your algorithm. Yes, and it's a recursive algorithm. In the base case, when n is 1, it just returns 2. In any other case, what it does is it calls itself at decremented argument, right? It's the same argument, but minus 1. And whatever this gives, it multiplies by 2. Well, this is exactly the same thing, right? Power 2 of n is also 2 to the n, because basically these are all the same objects. I mean, this Sn is equal to f of n, and the power 2n is also equal to Sn, is also equal to f of n. Okay, it's the same thing. No. Okay. Here is one more type of recursive definitions. You've seen basically 3 types, and here is another one. Well, we can also use recursion to define a set, not a function, not a sequence, not an algorithm, a set. Okay, so let's say we call that set S. That this is arbitrary. That we call that function F. We could have called it G or H, and this sequence, it could be A, B, or whatever, right? This name of the algorithm doesn't matter. The name of the set also doesn't matter, but we have to fix it so that to have a simple notation. Recursive definition of some set S contains 2 things. Something called the basis rule, corresponding to the base case of all of this stuff. And the basis rule will say that you specify some elements of S explicitly. Okay, explicitly. In other words, you just declare some elements to be elements of S, just like here, you just declare this value to be the first value of the function, or the first value of the sequence, first element in the sequence, or what directly you define the output of this algorithm for this base case instead of in terms of previous, right? And then you have a recursive rule, or perhaps many such rules. And these recursive rules specify new elements of S as functions, as function or functions, if you have several rules, of existing elements. Okay, well, this is similar to, you see, you assume that some formula, either the base case or, well, this recursive case, already define the value of this function at n-1, and now you're using this recurrence relation, recursive formula to define the value at one more point. Or you assume that this sequence element was defined, and now you use this formula to define the sequence element at some new index. Okay, is here too. You assume that there is some element in the set, and you'll use recursive rule to define new ones. And there is also formally you need something called exclusion statement, which is always the same. It just says S contains only elements added by either 1 or 2 rules. Okay, so you see, this means you add some elements are in the set, and this means that if some element is in the set, then so is some other. but that doesn't exclude that you can add some elements to the set, okay, that are yet came to the set in some other way. So we say no. The only elements are those built in this way. You don't have to repeat this. It's always you think of this as implicit. Okay, we'll never ask you to repeat this stuff because it's always the same. Okay, let's look at some examples. Okay. Let's look at examples. So, okay, let's keep this blueprint for a sec, so we see it. Okay, and let's exemplify it now. So, how about this? Use the following. How about this following recursive definition of set S? The base rule is that 0 is in S. So here I mean integer 0. That's the base case. And the recursive rule says if some element X is in the set, then so is 1 plus that element. Okay? It's an example. This is an example of the base rule. I'm declaring some elements of set S explicitly. Well, this is the one. 0 is an element of set S. The recursive rule specifies new elements as function of existing ones. Well, if this is the existing one, this is a function. You take the existing one and you add 1 to it. Question, what is S? Okay, the trivial answer is that S is whatever is defined using this recursive definition. That's a good answer, but you will get 0 points if you give me this answer. Okay, so it's not a good answer. Okay, it's a it's a stupid answer. All right, it's true, but it's meaningless. It doesn't show any understanding of this. So when I say what is S, I mean give me a non-recursive definition of this set. Okay. And the answer is okay. Let's see. Okay, so how do you tell what is this? What set is built by this? Okay, so here's the general blueprint for how you can you work with recursive definitions. Tell yourself how many times you using the recursive rule to build elements into the set, because set S contains everything that is built by these rules, either the base or the recursive. Okay, so these will be the new S elements, and here I will be, the current state of S. Okay. At the beginning, we say, okay, don't use the recursive rule. Well, you just use the base rule. That's very simple. So what's in the set? 0. So the current set, well, it just has the 0 in it. Let's say we want to use the recursive rule now. How do we use it? The recursive rule says, if something is in the set, then so is 1 plus that something. Okay, well, what's in the set? Just the 0. So the only way to instantiate this, that something actually happens, is when X is equal to 0. Okay, so if X is equal to 0, then what is the statement says? It says that if 0 is in S, then 0 plus 1, which is 1, is in S. Now 0 is in S by the base case, so therefore 1 must be in S. So therefore, actually S contains 0 and 1. Let's use the recursive rule once more. Okay, now if you use this rule and you instantiate what's in S, 0 and 1, you know that for sure. You know that 0 is in S by the base case rule. You know that 1 is in S by single application of this. If I instantiate X again with a 0, well, this X plus 1 is going to be 1, so I will not add anything new to the set. But if I instantiate X with 1, then this formula says that if 1 is in set S, then so must be 1 plus 1, which is 2. Now 1 is in the set. Therefore, I must add 2 in the set. So the set really is this. And clearly, I recurse, right? So the third time I apply the recursive rule, again, these guys will give me nothing more, nothing interesting. But if I instantiate X as 2, then this rule says that if 2 is in S, then so is 3. So I must add 3. So therefore, the set is like this. And if you go on, right, then at step N, what you are adding is N. And so the set is going to be look like this. And if this is a set after N applications of recursive rule, then what is happening when you do it one more time? Well, the interesting thing will be if X is N, because then you will add N plus 1, and therefore the set will be this. And okay, and now can you say, what is this set? If every application of the recursive rule seems to have added yet another integer into the set, then I'm claiming there is a unique set, only one, which satisfies these two constraints. Okay, for which both of these statements are true. There is only one such set. And let me give you a hint. This is not it. Because which rule does it not satisfy? This one. It satisfies it for all integers from 0 to n, and it also satisfies it for all elements that are outside of this, right? Because the statement, if -3 is in the set, then so is -2, is true. -3 is not in the set, so the statement is trivially true. There is one element, though, that this is not satisfied for, n plus 1. It is in the set, but n plus 2 is not here. So neither of these sets is the true S. It is just an intermediate S that tells us, so this is not the real S, right? None of these sets satisfy this. What is the one set that does satisfy it? Use chat. Yeah. N. S is N. Okay, i.e. S is the set of naturals or non-negative integers, right? Because that's the only set that's going through. Will this set satisfy it? Yes. 0 is in it, good. And if something is in it, then so is that thing plus 1. It is true about this infinite set. And that's the same logic. Why did this recursive formula define a function for all integers, for the infinite domain? Because for any integer, we can run it in the loop and get that. Why does this recursive formula define all integers? Because any integer will be eventually reached by this recursive rule. Okay, so it's the same reason. Okay, let's try something else. Okay, so how about this? Define S So these are examples, right? So this is the first one. Let's do another one. We changed the base case slightly. I will do that one is in the set. And I changed the recursive rule to, if X and Y are in the set, then so is X plus Y. Okay, and that's it. My question, as always, what is S? What set was defined in this using this recursive definition? Okay, so well, let's try it. Okay, so here is the number of recursive rule. I mean, and by the number I mean how many times have I used the recursive rule? Okay, the new S elements and the the state of S. Okay, which is sort of an informal notion, but I mean I can formally define it by saying what elements are created by up to n applications of this rule. Okay, and that will be the state of S in the nth row. So okay, so let's start with the base case. What's in the set? Well, 1. So for now it's okay, let's try to use this recursive rule. Okay, so if X and Y are in the set S, okay, so what could these X and Y be? Well, actually one thing, they're both 1, because that seems to be the only element in set S so far. So both X and Y are 1. What's X plus Y? So therefore it's 1 plus 1, so it's 2. So the set is like this. Let's use the rule again. If what could be this X and Y's? Well, this is your set S so far. So X and Y could be 1. That's not interesting, because then X plus 1, Y is 2, which we already built. Well, X could be 1 and Y could be 2, in which case X plus Y is 3. But also X can be 2 and Y can be 2, in which case X plus Y is 4. So it seems that after the second usage of the recursive rule, and by here I count, I guess, here I use the recursive rule, and here I use it again. The point is that in order to reach this element, how many times did I need to use the recursive rule starting from the base case? 2. I start with the base case, then I use recursive rule once to build a 2, then I use it again to build a 4. Okay, so you basically, these are like trees of if I think of this as tree, then the number of pops I have to go through in order to reach all of these guys is 2. Okay, let's use the recursive rule now again, applied to all of these. What are we adding? So X and Y are elements here. What would be the interesting cases that do not duplicate, right? Because we can always duplicate. Adding an element to a set that already exists in it does nothing. Okay, so it doesn't double this element in the set, right? It doesn't remove it either. It does nothing. Okay, so in order to actually build something new, well, let's make X, I mean, the best is to make Y equal 4, right? And let X range. X equal 1, X equal 2, X equal 3, X equal 4. What are you gonna build? 5, 6, 7, and 8, right? And you cannot build anything else, basically, right? Like whatever, you go from the minimum to the maximum, and you see that you get integers between 1 and 8, or actually 2 and 8, but 1 is still there because the base case. So So it seems that after 3 applications, you did this, and well, not hard to see what will happen after 4th case, right? You will just get everything from 9 to 16, and right, because you're basically doubling everything, right? You're getting everything that is the max plus 1 all the way to the max. So what's the new max? It's twice the old max, and you get everything in between. So if you did this recursively, right, like it seems that at n step, what you get is everything from 1 to the n. So what is it? What is that set? It's Z plus, right? i.e. S is the set of positive integers. This rule seems to build stuff sort of exponentially faster than this one, right? This one, in order to reach any one, an element n, I have to use make n hops. Here, after n hops, I seems to reach everything between 1 and actually 2 to the n. In some sense, this is more efficient. If I started with a 0 here, what would happen? What would happen if I didn't have a 1 here but a 0? Come on. No. Yeah. You would just loop in place. Okay, no problem. For those who are just viewing on YouTube, I'm replying to chat messages, and you don't see these chat messages. So students come up, it's just a 0, right? Like, so if you start with a 0, then adding a bunch of zeros just always gives you a 0. So you're never adding anything new. Yeah, right? What would happen here if I start with a 1? You would define the same set, right? Z plus. Just define it slowly, more slowly in some sense, right? If you start with the 1 here, okay, so which of these definition is correct for Z plus? So imagine that you start from 1, and therefore this becomes not n, but Z plus. Is there any problem with that these are 2 different recursive definitions which get you the same set? No. Just like there could be many recursive algorithms that compute powers of 2, right? I mean, just last lecture we showed 2 exponentiation algorithms with vastly different performance, one linear, the other logarithmic in the exponent, both correct, but both defining the same outputs, but different as algorithms. Let's look at some other examples. Okay, how about you do this? Define S like this. The base case is 1, and the recursive is if x and y are in the set, then so is x minus y. Okay. Then, well, our question, what is S? Okay. Well, let's see. So here we have this, number of rec rules used, new S elements, and state of S. Okay. So let's, okay. That great focus. Let's prove it. Okay. maybe better. Okay. So, okay, the base case trivial is just 1. Let's use this once. Okay, so x and y are, well, there is just 1 in the set. So the only way to instantiate both x and y is to make them both equal to 1, at which point this becomes a 0. So actually, we were adding a 0. So now the set actually has 0 and 1. Okay, what gets added when you run this again? So now x and y's can be 0, 0, 0, 1, 1, 0, 1, 1. Well, if they're both 0, 0, then you're just getting a 0, so nothing new. If they're both 1, 1, you're getting a 0. If this is 1 and this is 0, then you're getting a 1, which you already have. But if this is 0 and this is 1, you got -1. So the new thing that you added is -1, right? So that got added with x equals 0 and y equal 1. Okay, so the set is actually this. Okay, what about one more time? So now x and y's range over this. What new thing can you add that, well, so basically, let's try to make x maximum and y minimum. Okay, so if this is 1 and this is -1, then what you added is 2, right? So that was for maximum x and a minimum y. Let's switch, make x minimum and y maximum. So this is -1 and this is 1, so it's -1 -1, it's -2. So that's for the switch case. X was -1 and 1 was 1. So the set seems to be like this. And you know, can I get anything new? Well, you can see that, you know, however you range, you basically cannot go further than this range, because, you know, the smallest element that you can add really is make this minimum and make this maximum, and the largest make this maximum and make this minimum, right? So anything that you add in between must be between these two, but they were already in there, so you're not gonna add anything new. Okay, but when you do it one more time, actually you will see that you can add -4, -3, and also 3 and 4. So this becomes from -4 to 4. And okay, and now can you already start perhaps guessing what the set is going to be, right? Because the next time we do it, if you do the same logic of minimum maximum, you know, the maximum element you're going to add is 4 minus 4, which is 8. And the minimum is when you take -4 and you subtract 4, which is going to give you -8. And you can do everything in between, right? Because if everything in between is covered, then you just move this guy slightly. What it means is that the result is shifted by 1, right? So the next time you do it, you're gonna get everything between -8 and 8, and so forth. So it's like this, except that minus is included. So it is what? Come on, come on. Don't wait. Yes, good. Z, all integers. Right, negative and positive, right? So, you know, the kind of, I think, beautiful, somebody can think, you know, nightmarish aspect of this is that these little rules are sort of very small, and they don't differ by a hell lot, right? If you focus on, you know, these basic, you know, this set of base recursive, base recursive, base recursive, the variance is, you know, really tiny, right? And if you don't think about what this does, if you don't understand how to use it, then you might make, or simply, yes, we all make mistakes, right? So you could, if you're sort of too fast in, declaring that understanding, you might sort of say, okay, this define all positive integers, so maybe this will define all negative ones, right? I mean, this seemed to work for starting from 0 to create all integers. Maybe I can start from 0 and use this thing and do the same. Well, actually, they are very sensitive to both what you start with and how you proceed. And it's the same thing when you have recursive code. It can do beautiful things, like search through a list or sort a list or solve a lot of problems that look hard and insurmountable even, but with recursion, suddenly they become, maybe I would go as far as to say, somehow clear. Okay, not just doable, but also, like, of course doable. Okay, and so that's the power of the stuff. It's small. Tiny changes can make huge differences, but at the same time, it is also very powerful. Not sometimes not trivial to see. Okay, like, what is this doing? Okay, maybe how about this example? What if I modify this like this? 1 is in S, and if x, y are in S, then so is x plus y, and also x minus y. So like a sort of union of these two rules, right? I could write this rule simply by having both this and that, because this implication is the same as conjunction of this implication and this implication. Simply, if you say if A, then B, and if A, then C, then it's the same as say if A, then both B and C. What is S now? Though I don't know if somebody answered, it was positive here. It is all of them here. Which of these two cases will I hit if I modify the recursive rule like this? Yes, it should still be okay, because, well, I mean, intuitively, what is this part, this rule? What is it doing? It's just adding sums, and what this will create is Z plus. This rule seems to be adding both differences and sums, because if I put negative numbers here, then I basically end up with a sum, right? So that's why it basically built both negative and positive integers. You can test this set satisfies this both. Okay, the base case, obviously, yes, because Z includes 1, and this implication, does this set satisfy it? Yes, it does. No matter what xy integers there are, the sum of them is an integer, and the difference between them is an integer. So a check, which you should always do, that your answer does satisfy both, the base, these two requirements, is a necessary check. And actually, once you make this, it's kind of simple to check, right? You can, the check is not the whole answer, because if my answer here was real, which is a superset of integers, right? It's a set that is to which integers are a subset of them. The reals would also satisfy both of these. One is a real, and for any two reals, their sum and their difference still remains a real. So checking that these are satisfied doesn't tell me that my answer is minimal. And that's the role of this exclusion statement. The two rules might be satisfied by supersets of your solution. Okay, so instead of, the solution is integers, a superset, for example, I can take rationals. Both of these would be satisfied, but the exclusion statement will fail. There is no way to start with an integer and then consider sums and differences to build a non-integer rational, right? Okay, but checking that the constraints are satisfied for your answer is a sanity check. Questions on this? Because I don't think this is such a trivial stuff. I mean, Okay. Let's exemplify it in some with more examples. So I guess that's example fine. How about the following set defined recursively? The base case, I'm going to say lambda is in the set S, and recall lambda is an empty string. So it's a special symbol that we use to denote an empty string. We've had strings sometime, a few weeks ago, so this is just a recall. And recursive rule is the following: if x is in S, then so is x is 0 and x1. And here, what these two things is, they stand for concatenation of x with respectively 0 and 1. Okay. On the test and so forth, we will try to disambiguate, right? But if you see something like this, you should know that it's a concatenation of strings. Okay, this is not a multiplication of x with a 0, or it's not a multiplication of x with a 1. Yes, these are not interesting operations. Okay, but the string concatenation is. Okay, let's see what is being built here. Okay, so number of recursive rule applications and new S elements. Okay, so say I'm in the base case, I don't use recursive rule at all. What is in here is an empty string. Okay, I use this rule once. So x is an empty string, right? The only way to instantiate it so far. So what is an empty string concatenated with a 0? It's a string with a single 0 in it, right? Because an empty string concatenated with something is that thing. Empty string concatenated with 1 is a bit string with a single bit 1. Okay, let's use the recursive rule again. So now x, of course, if I apply it to this guy, I'm just going to recreate 2, so that's not interesting. So let's apply x to 0. So if x is 0, then what is being built is a string 0, 0 by this rule with x instantiated with 0. And this rule with x instantiated with 0 gives me this string 0, 1. X is a 0, so x1 is 0, 1. If x is 1, then what do I get? 1, 0 and 1, 1. Okay, and maybe you can see that, right? Like the third time I do it, the x is any of guys, and I'm basically adding a 0 or a 1 to whatever x is. So what am I gonna build? Basically all, all bit strings of length 3, right? Etc. So what is S? That was a question, and an answer is that S is every recursive rule, every application of this rule adds n. Okay, good. So somebody answered, well, what they answered is really should be here, that after n applications, you're going to build the new stuff is n bit strings. And, after n-1 applications, what you have added is n-1 bit strings. And so what's the union of, so it seems that S is a union of n going from 0 to infinity of bit strings of length n. That has a special notation. What is this? Yes, it's all bit strings. But do you remember how to write it in this fashion? Anyone? Okay, I'll not wait for you. It's this 0, 1 to the star, because that stands for this thing, a union, an infinite union of bit strings, of strings over this alphabet that are of length n. Okay, and that just simply means all bit strings, including an empty one. Okay. 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 Here is something else. Okay, so if I did this, so lambda is in S, and if x in S, if x and y in S, then xy in S. It's kind of like this, right? I either build new bit strings slowly by just adding a bit to it, or perhaps I build them fast by concatenating existing bit strings, kind of like adding existing integers rather than just incrementing 1 to every integer. But this will fail, right? Because the only thing is an empty string, and if I instantiate it with empty strings, I concatenate two empty strings, so I just get an empty string. So I guess I have to change this and perhaps say this. Okay, so I declare an empty string to be an element, a 0 to be an element, and a 1. And now I'm game, because well, the base case now becomes this. All right. And now what is added into the, so, well, let's see. So this is the number of recursive rule applications and set as new as elements. Okay. So in the base case, I get lambda 0 and 1. I use it once, and what do I get? Well, any combinations of the stuff concatenated. So I'm gonna get all bit strings of length 2, right? Now I use the recursive rule again, meaning my x and y's can be anything in here. So x can be well, empty is not interesting because that doesn't change anything. But if x is a single bit, y can be any 2-bit string. So I'm gonna get, all 3-bit strings, right? But well, if x is a 2-bit string and y is a single bit, I'm gonna get these guys again. And if both x and y are 2-bit strings, then I'm gonna get all 4-bit strings. So if you basically think like this, what you're gonna get by step n is actually all bit strings of length 2 to the n. Okay, which means that S is again the set of all bit strings. It is just built faster, right? In the same way as this, as this code, right, where you add it was faster, quote unquote, than this one where you just increment it. It's the same difference. Here you build new guys by just adding a single bit to them. Here you build new guys by concatenating existing ones. But in order for that to work, you had to, set the base case carefully, or otherwise, if you eliminated both of these, right, then this would just have loop in place and build nothing new. If you eliminated one of them, then you will just get, bit strings containing 1 only, right? So a bit string of arbitrary size, but it just has copies of 1 or copies of 0. But just adding them both means that you now build every bit string. Okay. Okay. Let's. How about this? Let's up the ante a little. So here is my case. 0 is an element of S, and I will have 2 recursive rules. If x0 is in set S, no, you know what? No. If x is in set S, then x0 is in set S. So it's like this, but I'm omitting this rule. But I'm also adding another one. If x0 is in S, then x01 is in S. So, I mean, if you want to call it, this could be 2A and this could be 2B, right? Because we said you might have many recursive rules. I have 2. In fact, that's nothing new because this type of statement hides essentially 2 recursive rules. If x is in S, then so is x0. If x is in S, then so is x1. These are really 2 rules. And here I have 2 rules. If x is in S, then so is x0. But if string, which can be represented as x0 for some x, of course, these are not the same ones, right? Like it cannot be. But yes, same, there is no x such that x is equal to x0. Yes, just like there is no x integer such that x is equal to x plus 1, right? This will never work. But this doesn't matter because these are if-then separate clauses. I could maybe, for your, mental health, I could use a different variable. You know what? Let me do it. So, you guys don't get completely crazy. And let's just call it a Z. All right. But there's really no difference, right? Because it's just like 2 pieces of code. They are welcome to use any variable you want. In particular, this rule can use the same variable name as this one, and there's no clash. Okay, if this is our definition, so let's repeat this on a fresh piece of paper. So this is the 7th example. Define S as the base case 0 is in the set and 2 recursive rules. If X in the set, then so is X0, and another rule, if Z0 is in set, then so is Z01. Okay, so let's see what this creates. Okay. Okay, so let's maybe leave some good amount of space. So this is the number of recursive rule applications, and these are new S elements, and this is the state of S so far. Okay, so let's start easy, base case. So what's in the set? Well, easy, just a 0. Okay, so it's a single bit string, 0. Let's use the recursive rule. Which of these two rules can we use? This one? This one, actually, we can use both. So if you use, you know what? Let me call it 2.1 and 2.2, because then it's gonna be easier to refer to them. So these are two recursive rules. Okay, the first one and the second one. So if I use the first recursive rule with X0, then what do I get? Because only there is X in the set, X0. Well, I got 0, 0 as a new element, right? Let's use the second recursive rule with Z0 equal to 0. Because there is an element in the set that can be rendered as Z0. It's this one. And what's Z? It's an empty string. So here Z is an empty string. And if Z is an empty string, then what did you add here? You added 0, 1. Okay, this rule, did it match? Is there an element in the set that can be viewed as Z0 for some Z? Yes, this guy for Z empty string. And therefore, what you're gonna add is an empty string 0, 1, which is 0, 1. So what is the state of S? 0, 0, 0, 0, 1. Let's see what we are adding now. Okay, so of course, we can always use the recursive rule 1, okay, because that one has basically no conditions, so to speak. This, you can think of this as a condition. Not every element of this S is of that form, but some are, like this one is. Okay, if we try to, but this one is an unconditional. Whatever element is in S, that element with a 0 is also there. So let's apply it to these guys. Well, this one not gonna create anything new. So let's use it with these new guys, 0, 0. What are we adding? 0, 0, 0. If we use it with this string, we're gonna add 0, 1, 0, 1, 0. Now, can we use the second rule with anything? Which of these elements is of the form Z0 for some Z? Well, this guy for Z empty, but that was already done here, and we added this. The only other is this. And what's the Z? It's the Z0 is 0, 0. So therefore Z is 0. Yeah, that thing, it has a form Z, this form for Z equals 0. So what are we gonna add? 0, 0, 1. So we will add 0, 0, 1. Sorry. These are the three elements added. So let's add them here. So what do we have? It's 0. Wait, no, wait a second, wait. Hold on. Yes. 0, 0, 0, 0, 0, 1. And what 3-bit strings we have? Now what? Let's write them this way. So it's a single bit string is this. The 2-bit strings are these, and the 3-bit strings are 0, 0, 0, 1, 0, 0, 0, 1. Okay. Okay. Let's do this again. So what can we do? This rule, what will it do? Well, it will just add 0 to everything. Adding 0 to this is already here. Adding 0 to this is already here. And adding 0 to this is already here. So we add zeros to these guys, and what are we create? 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So that will be using rule 1. And now if we try to use rule 2, we can apply the rule to everything that has this form, z followed by 0. Which of these two is this? These two guys have this form, right? So where the z part is 0, 0 or 0, 1. So what are we going to add? Well, in the first case, it's z is this, and we are adding 0, 1 to it, so like this. In the second case, z is 0, 1, and we are adding 0, 1, so like this. So now the state of is, well, we have all the stuff as before. The 3-bit strings are these, and the 4-bit strings are 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1. Does anybody have a hypothesis of what is being created here? So what is set as? Well, let me say this. S is a set of all bit strings that start with bit 0, and they satisfy a certain constraint. Think of what this basically does. Whenever you have an x that you can always add a 0 to it, but you cannot always add a 1. You only add a 1 if the string had the form that it ended with a 0. Then you can add a 1. No other way. So what this says is that, well, zeros can occur freely, but for 1 to occur, it has to be preceded by a 0. In other words, you cannot create this string, right? Because if something ends with a 1, then you have to add a 0 to it. That's the only way to make it grow. At this point, you can add both 0 and 1. But from here, you only can grow to, you only can put 0, where here you can put anything. So what is this constraint? Yes, exactly. And so they start with a 0 and contain no 1, 1 substring, right? So they cannot have a run of 1s yes, they yeah, okay, they contain no substring 1, 1. You can argue this by recursion, by induction, that so there's two things to check. Is all strings in the set, are they built using this? And the second thing to check is, are only strings in the set that are built using this? So that only strings like this are built using this is an easier direction, because we, by induction, by how many times we use the recursive rule, we can argue this relatively easily. The proof would go, well, if you don't use recursive rule at all, clearly you are in the set. And if you have used it n times, and n usages of recursive rule was constrained to the set, then would the n plus first usage of the recursive rule still keep you in the set, or will it go outside? And that's an easy thing, because if n usage of this, if both x contains no substring like this, I mean, if it satisfies this, then adding 0 to it is still clearly within the set. And if this string contains no ones, starts with a 0, then of course adding this doesn't change its beginning, so it's still a string that starts with a 0. And if it contains no runs of 1, well, you didn't create a run of 1 by doing this substitution, right? So it's still within the set. The argument that only that all strings is more complex. Okay, so and I'm not prepared to do it, so I won't do it. But I would think about what how one would do it, and I recommend you to think about how you would argue that all strings of that type are going to be created by this rule. Okay. Another thing, so here is a good exercise. I think how to argue that all strings okay, here is the recursive definition of S, and here is a non-recursive definition. So in order to prove anything about them, let's call this that all strings that such that this requirement is satisfied are in set S, which is defined here. Okay, I claim that the opposite, that only these strings are in the set defined here, is an easier direction. Okay, give a recursive definition for set of all bit strings that contain no 1, 1 substring. This one is not that, it's all those, but with the constraint that they have to start with a 0, and that's because we started with a 0. Okay, well, how would you do all of them? Okay, maybe simple, maybe. Okay. Okay. Well, I guess so. How about containing no 0, 0? Okay, but perhaps that should be simple, right? Because clearly just change zeros and ones, and you should have a symmetry. Here is another example. Let define as, which example is it? Okay, doesn't matter all that much. I guess it's example number 8. Define as like this. The base case is that the following string is in the set. It's so this is a string of 2 characters, open bracket and close bracket. Okay. The recursive rule will be, there will be 2 recursive rules. So recursive rule number 1 will be that if some string is in the set S, then so is this string, whatever string that was, but prepended with an open bracket and postfixed by the open bracket, by the closed brackets. And a second recursive rule is that if I have 2 strings in the set, then if I concatenate them, they're still in the set. What is this set? Okay. So it says that open close bracket is a sort of, let's say what the set S is going to be. I'm just going to say these are good expressions. Okay, good strings. I'm just saying that S contains, I'm just going to define a string good as the string belongs to set S. So this says that open close bracket is a good string. This says that if some string is good, then if I put it inside of open close bracket, then it's also I declare it to be good. And 2 good strings can be concatenated. S is a set of properly nested parentheses strings. So if you okay, so this is the standard thing, how many times I use the recursive rule, and what elements, new S elements, right? A new S element and state of S. So at the beginning, I have this thing, so this thing is in S. Then I use the recursive rule. So what's A? Well, A is this string. So this thing is going to be in the set S, right? Because I took my string open close bracket, and I prepended with the open bracket, and I postfixed it by a close bracket. Now, so that came from rule 1 for A. This can I use this rule? Yes. If I use rule 2 with A equal B equal this, right? Because indeed that's the only way to instantiate. The only thing in the set is open close bracket string. So both A is the string and B is the string. Then so is concatenation. So this string. Okay. So the state of S is okay. I have this inside here. I have this string inside here, and I have this string inside here. If I use the recursive rule now, well, I have more choices. So, well, if A is this guy, then I'm just gonna build this guy again. Okay, so let's instantiate A with this. So recursive rule one, I can instantiate this, so, and it's gonna create me this thing surrounded by open close bracket. So it's this string. And if I instantiate A with this, what does the first rule gonna build? It's gonna build open, this thing, open, close, and then close. Okay, what about the rule 2? Well, these are just concatenations of stuff. So let's concatenate everything with everything. So this with that gives me this string. This with that gives me this thing. This with that gives me, okay, and I guess this with itself, but this with itself gives me only this. So, okay, so let's now start with this and concatenate it with, okay, so if I take this and concatenate with this, I'm gonna get that. If I concatenate this with itself, this is the case where both A is equal to this and B is equal to this, I'm gonna get open, close, open, close. And if I concatenate it with this, I'm gonna get open, close, and this thing, open, close. Right, okay, finally, I take this and concatenate with that. Well, this is gonna get me this again. I take this, concatenate with that. It's open, close, close, and this with itself, open, close. Okay, I'm not gonna copy all of this stuff, right? So, but this is, you know, just moves here, and this of course stays here, right? And we will stop here, right? Obviously, because this gets really complicated, right? Like, I mean, you basically, these tiny rules end up building very complex things where just like looking at them, you're like, you know, oh, you know, did it build all open, close with the particular length? I'm not sure. You know, they seem to differ by length, right? And of course they would because of this rule, right? So, but if, this is a set of all properly nested parenthesis strings. In other words, and what is a properly nested parenthesis string? So it's something that has, well, if, you know, so here is like something not in the set. Open, close, and that's it. It's not properly nested. I opened, inside of it, I opened and closed, but then I didn't close. Now this is properly nested, but perhaps I opened, close, and then opened again. And how can I continue? Well, I can close and close, but perhaps I opened another one, and now I closed this one. And perhaps I opened another one and closed this one. And now I closed this, and now I finally closed that. You can see that there's many ways to go. In fact, if you were to describe a code that would say, okay, you know, any piece, so properly created code, right? Like if you have a bunch of if-then expressions, they kind of can be mapped to, you know, what's the end of the clause? Okay, you know what? Think of Boolean expressions. Okay, if I have a Boolean expression, I better have, you know, if I'm using and something or something or A implies and I open, then I better close this one, right? So the problem of recognizing correct Boolean expression is not easier than a problem of just recognizing properly nested parenthesis strings, because a Boolean expression has to, in particular, have properly nested expressions inside. And even writing a code that recognizes whether an expression is a correctly formed Boolean expression, or even simpler, for correctly formed parenthesis strings, is not obvious. You know, if you do a linear scan, would you be able to write a code that will determine whether it's correctly formed or not? But here is a definition that hits all of them. Okay, you can think of this definition as a way to generate all parenthesis strings. It does generate all of them, and it generates only them. You cannot generate improperly, parenthesis strings using these rules. But perhaps this is not the most okay. But another way to look at the recursive definitions is that they can be used not to generate something, but to recognize something. So how do I use these rules to test whether a given string is a properly formed parenthesis expression? I take the string and I recurse sort of backward. I try to make the string into either generated by this rule using some other string, which would be, okay, well, my hypothesis is that perhaps this whole thing inside is an A. And I generated this big thing by taking some A and putting an open and closed brackets over them. And then I use the same recognizer recursively to test whether A is a properly nested string. My A now is smaller. So this recursion is going to eventually tell me yes or wrong or no. Unfortunately, because this rule is like this, maybe a given string was created using this rule. Maybe a given string has a parsing of some A followed by some B, such that both A and B are generated using the same rules again. Why did I say unfortunately? Because when you are given a string S, then you can say, well, this is A, this is B, or perhaps this is A, this is B, or perhaps this is A, this is B, and so forth. And if the string S has length n, unfortunately, you're going to have n choices. Which means that if that's your recognizer, then you're going to run this recursively n copies of this of the same recognizer applied to, yes, shorter things in every case. However, a call to recognize S created n calls to recognize first substring and the rest. Yes, here is basically I had n ways to split them up into A's and B's. And, this is, so it's not an efficient way to recognize because, at each step you're going to write, like if you had n splits here, and maybe if you're lucky, it's n-1, how many paths are there? A lot. Kind of n factorial, right? Okay, that's not good because that's exponential in the length of the formula. Okay, but at least we are starting somewhere. At least for some complicated stuff which we do need to do, like recognizing properly formed Boolean expressions, recognizing, right? So as a piece of code, you can see it does need to have this structure, like things XML or other languages. They're in particular a bunch of instructions that are looped in this way, okay, grouped in this way, and whether they're proper or not, well, clearly is important an interpreter or compiler in particular must perform that and recognize, whether something is properly formed or not. So these little pieces of recursive definitions is the start of the process of building these and also recognizing them. And of course, we're not talking about efficiency in this class, right? But that's you will see these things again when you see how compilers interpret pieces of code and parse them. Okay, many of these examples are in the book. You can check them there. I'm running a little late with the material, so I will think like whether maybe I will post another lecture on this stuff, because like one, definitely examples using binary trees is something that you should look at, and I think it helps to see them, not just in a book but live, quote unquote, right, in a lecture. So I'll also ask the TAs to focus on these examples at discussion on Monday and Tuesday next week. And I guess I'll just post a lecture, so you can not just read this in the book, but also listen to it if you like. Okay. Sorry to go a little longer. I will stop recording, and but you can still ask questions.